everyone, in this problem we will be finding the area of the part of the hyperbolic paraboloid z equals y squared minus x squared. That's the first piece of information we need because we need to take the partial derivatives of y squared minus x squared. So let's write it down. So the partial derivative in terms of x, we're turning y as a constant. So it's like we're just having negative x squared. And that would be negative 2x. Don't forget the negative. Now the partial derivative in terms of y, that's 2y. Now our second step, we will be plugging our information into the formula. So it would be 1 plus negative 2x squared plus 2y squared. It's a good idea to simplify it right away. Giving us 1 plus 4x squared plus 4y squared. Our third step would be graphing. So it doesn't have to be perfect, but just so you are understanding what region we are really caring about, because we might have extra stuff that we don't need. From the question, the cylinder x squared plus y squared equals 1. That simply is a circle, right? And the second one, it's another circle. X squared plus y squared equals 4. Therefore, the region we're truly caring about, it's what's in between those circles. All of this. Not the inside and not the outside. So now that we know we have two circles, we should automatically think of polar coordinates, because this will make the process a lot easier. Therefore, we are defining our parameters in terms of r and theta. The first circle has a radius of 1. The second one has a radius of 2. Square root of 4 is 2. Again, we are only caring about what's in between those circles, so only this. The radius is between 1 and 2. That's exactly what goes here. Our theta is 0 to 2 pi because it's covering the whole circle. Now we just have to solve. So we have our double integral, and as we mentioned, we are using polar coordinates, so r dr d theta. R is in between 1 and 2, theta is in between 0 and 2 pi. We just bring down what we got from the square root. Now, it is very important to write everything in terms of r and theta. And we have some x's and y's here. What we can do is, since we have a 4 common to x and y, bring it outside. So you have x squared plus y squared here in parentheses, and we know that x squared plus y squared equals r squared. So let's replace the r squared right here. Since we have an r here outside, we can use substitution to get rid of it. So our u, it's what's inside the square root. 1 plus 4r squared. We take now the derivative of both sides, giving us 8r dr. We divide 8r, now allowing us to cancel the r with the 8r. We can now write the new parameters of integration by plugging 2 and 1 into the equation right here. I like to draw two lines to represent what goes at the top and what goes at the bottom. So once we plug in 1, we are going to end up with 5. And once we plug in 2, we end up with 17. Also remember, we are left here with 1/8, so that needs to still be carried over. So 1/8. 17, square root of u. Square root of u is the same thing as u to the 1/2, so it's a little bit easier to integrate. And also we can technically split this into 2, and you'll see that it's the same process. Like, you can continue like this, but if you split it, the math will be a bit easier. Therefore, it's just like integrating theta in terms of 2 pi and 0, and we're integrating this separately, where we end up with 2/3 u to the 3/2, and we are plugging u so we get 1/8 2 pi. Now 2/3 will be common to both, so we can take it out and keep in parentheses 17 3/2 minus 5 to the 3/2, giving us, well, this is just saying pi over 6, and this, if we simplify further, we are left with 17 square root of 17 minus 5 square root of 5, and this would be our final answer. If you like this video, please subscribe, and I'll see you in the next one.